We're going to do a problem, an example or two examples, and make two different videos for some contact stress, and then we'll do a bunch of examples as part of our review of what we've done thus far here at, because we're at class 8, and we're going to have an exam in a little while, soon. So we need to have the stuff that was testable material, so give you some problems to like work through to see if you really understand the material, which is like always in addition. There's like voluntary stuff in addition to the homework. But here is a problem 3-136. We have a carbon steel ball with a 30 millimeter diameter, and it's pressed against a flat carbon plate with a force of 20 newtons. We're going to determine the maximum shear stress and the depth in the plate at which it will occur. So let's go ahead and do that then. I stick myself up there. Okay, no. There you go. All right. So things that we're going to need. Well, if we're looking at, we know that it's a carbon steel plate and it's a carbon steel ball. So those are equal to each other. Right? Those are the same things, materials that might make things easy. I went ahead and used an elastic modulus of 30 E6 psi. If you wanted to find this in the book, and I don't think we've covered this yet, but if you go to the appendices and you look right here in table A5, you'll find a lot of basic modulus elasticity, modulus of rigidity, and Poisson's ratio, and even unit weight of the stuff. And if we just go carbon steel, boom, we say that that has an elastic modulus of 30 million psi and a Poisson's ratio of 0.292, right? So I think I just went ahead and used a Poisson's ratio in my calculations here of 0.29. Should probably use a 0.292. But I'm also going to use that graph, remember, and that graph has a Poisson's ratio of actually 0.3. So there's a little bit of fudgy going on right here. These are not necessarily perfect numbers. But let's see. I'm looking at the wrong problem here, right? Oh, it's a 30 millimeter diameter. All right, so let me come back here. And carbon steel. And for whatever reason, interestingly enough, I decided to use 0.26 in my numbers, which is actually for Poisson's ratio. All right, so I said the steel had 200 gigapascals as its elastic modulus, and Shigley used 207, and I used in my numbers 0.26, and Shigley is saying 0.292. Here. I think I might have been following the solution manual when I wrote these out, which don't seem to agree with the book. Let's double check that. Yeah, you'll see that the carbon steel is 207 right there, right? I think that's what happened here. Maybe I should fix that at some point, but maybe not. All right, so I'm going to write out the equation, or let's just look up the equation in the book. And so these are this is sphere on a plate. Right, so we have a sphere and a plate, but, well, what do we have spheres and spheres? Well, a plate is just an infinitely large diameter plate, right? I mean, sphere. It's just, D2 is infinity, its diameter. Well, just going to make that 0. So great, right? And we can see we have these material properties right here. If this one equals this one, we can shorten this up. Right there, right? So this, it's just going to be cube root of 3f over 8, and then 2 times 1 minus nu, whoop, that nu needs to be squared, divided by e, divided by 1 over d, right? everything else, these are both the same, and then the diameter of one of the other ones is infinity, so it's 1 over infinity, so it's 0. So we end up going cube root of 3 times 20 newtons divided by 8 times 2, 1 minus, and I got by 0.26 squared. That's divided by 2 e to 11, right? Because g is a e9, so that's 2 more decimal places. So we have 2e11 right there. And then divide by 1 divided by, it's 30 millimeters diameter, so 0.03. We get an itty-bitty small number, 1.280 e minus 4 meters, or, just to put it in perspective, 0.128 millimeters. You wouldn't be able to see that with the naked eye, but you could probably see that pretty well with a fairly good microscope, and definitely see it with an electron microscope, right? You could definitely see. So maybe we could even try to confirm that if we had some motivation to do it. And so we have our P max we can find now, which is 3 times f divided by 2 pi a squared. Remembering that a is the radius of my the radius of the circle formed between the sphere and the flat plate. And so it's going to be 3 times 20 divided by 2 pi, and then this really small number, 1.280 e minus 4 squared. And we end up, and I'm going to go ahead and just take out E6 of this, and we get a pretty large stress. And we'll see the contact stresses are actually really large. We usually use some other, and this is the maximum that's in there, but still, it's a fairly large number, right? And so, but we usually use some other criteria, not just the regular strengths in the books, to say what we have a contact strength that we compare contact stress to. So from the figure 337, reminding you that this is what we're using this figure right here, and we're really only using that guy right there and this guy right here. So the maximum stress is 0.3 times P max. So tau max, maximum shear, is 0.3 P max. 0.3 times 582.7 is written 174.8 megapascals. And the location of it is going to be Z is equal to 0.48A. Remember, that came from right here, 0.48A. So 0.48, and I'm plugging numbers in, which you could definitely do yourself. 1.280 E minus 4 meters, and turn them into millimeters. Might as well turn them into millimeters, right? Might as well just say 0.128 millimeters onto the thing. Put that in there so we could say that Z is equal to 0.0614 millimeters below surface. And that's going to be below either one, right? Either inside the sphere or down below in the plate, according to what we're assuming right there, right? So the tau max, just rewrite it out, 175 megapascals is the answer to this right here. And I compared it to my Excel plot and estimated that there's if I went ahead and adjusted for the Poisson's ratio that I had selected for that material, I got about a 2.5% difference in the location, and I got about a 6.4% difference if I used the correct Poisson's ratio, and instead of just using the and by the way, these are actually what the I found. I found a 0.468 instead of having a 0.48, and I found a 0.3193 was the maximum of those ratios instead of the 0.3, which gave me a bit of a difference. But you know, this is once again, we're trying to do our best with the tools that we have to assess what's taking place, and the trying to get any like a lot of decimal places and that kind of thing isn't really useful to us for our purposes. So I'm going to do another video, a separate video with the other example for this.